Hi everyone! So we are now going to discuss our fourth lesson here in Mechanics of Deformable Bodies, and that is about torsion. So this will be the first part of our discussion, and at the end of this discussion, students must be able to explain the basic torsional stress and deformation theory, compute torsional stress and the angle of twist when the body is subjected to applied torque, and solve engineering problems involving torsion. So let's start our discussion. Okay, so for torsion of circular shaft, let's talk about first the definition of torsion. So torsion, this is the twisting of an object due to an applied torque. Now, what is a torque? No, a torque, this is a moment that tends to twist a member about its longitudinal axis. Okay, so let's say we have here this circular shaft. Okay, this circular shaft AB. Okay, and as you can see here, this is restrained here at end A. No? Okay, and the other end, no? So this is free, no? Okay. So, class, no? As you can see here, there is an applied moment here. Okay, so this is an applied moment, and this moment, this is the torque. No? Okay, so this torque, no, this will cause this circular shaft, no, to be twisted. Okay, since it is fixed here, no, or restrained here at the other end, no, this end, no, wherein this is free here, no, it will be twisted. Okay, okay, so this twisting, no, will be about the x-axis. Okay, this torque T, no, it will tend to twist this circular shaft, no, about the longitudinal axis, which is the x-axis. Okay, so it will twist, no, in the direction of the torque. So it will twist clockwise. Okay. Okay, so its effect is of primary concern in the design of axles or drive shafts used in vehicles and machinery. Okay, so again, for this circular shaft, no, that is restrained in this end, no, and at the other end, so this is a free end. Okay, and after the application, no, of this torque T, no, what will happen is that this circular shaft will deform. Okay, and we are going to have an assumption here, no, about the deformation that will happen. Okay, so we are going to discuss that here, no, and as you can see in this figure, no, it shows the deformation of a circular shaft that is subjected to a twisting couple torque T. Okay, so class, just to visualize the deformation here, no, we are going to scribe line AB here. So as you can see, this is the line AB. So this is A and then B, no? So this is the line AB. Okay, so this is ano ha, these points are initially scribed here, no, before the application of the torque. Okay, and after we apply, no, this torque T, what will happen is that it will be twisted, no, it will twist clockwise. Okay, and what will happen is that this point B, no, it will be displaced, no, it will move, no, at this position, which is B prime. Okay, since the other end, this is restrained, no, so this will remain, no, this will not twist, no, the other end. So what will happen is that the original line AB, no, before the loading or before the application of torque T, after the torque T was applied, no, it will be displaced this way. No, so from point B, no, it will rotate, no, and it will be displaced here in this position, B prime. Okay, and the angle, no, the angle from point B to B prime, no, this will be the angle theta. Okay, and this angle theta, no, so this will be the angle of twisting. Okay, so that's the deformation that will happen, no, in a circular shaft, no, upon application or after application of torque T. Okay, so class, here in the deformation, our assumption is that during deformation, no, the cross sections are not distorted in any manner. So that means that it will not warp, no, it will not change in its shape, no, the cross section, this circular cross section, okay, it will not change in shape. Okay, it will not warp, no, and it will also not bulge in or bulge out. It will remain plain. Okay, so the cross section will remain plain. It will not, again, it will not bulge in or bulge out. Okay, and the radius r, no, so this is the radius r. Okay, so this radius r, it does not change. No, in addition, the length L of the shaft remains constant. So meaning to say it will not elongate or contract. Okay, so the deformation only here, no, in torsion in circular shaft is the twisting. Okay, or this angle theta. Okay. So each cross section rotates as a rigid entity about the axis of the shaft. Okay. Okay, so let's consider a differential element from this circular shaft. Let's say we take that differential element at this section. Okay, so this will be that differential element not taken from this section. So this is a differential element with circular cross section. Okay, so this has a radial distance of rho. Okay, and this has a width of dx. So this is differential or infinitesimal, meaning to say this is very, very small. Okay, this dx, this is very, very small. Okay, so from here, now as the shaft deforms, the two cross sections of the segment rotate about the x-axis. Okay, so from this element, no, this cross section, okay, so that cross section is here. Okay, and that and this cross section, which is the cross section behind here. Okay, so these two cross sections, okay, take note that they will both rotate, ha, as you can see here in the broken line. Okay, so they both rotated about the x-axis. Okay, and here, because the cross sections are separated by an infinitesimal distance dx, so this cross section in front, okay, and the cross section behind, no, they are separated by this very, very small distance. No, so this is an infinitesimal distance. So meaning to say, the difference in the rotation, okay, it will also be infinitesimal. Okay, so that rotation or the difference in their rotation will be denoted as d theta. So this is infinitesimal, ha, meaning to say this is also very, very small. Okay, so from here, as the cross sections undergo the relative rotation d theta, CD deforms into the helix CD prime. Okay, so originally, no, this will be the position of line CD, but because of the deformation or because of the applied torque, no, there will be a deformation here that it will be distorted into helix CD prime. Okay, and plus, take note here that by observing the distortion of the element in its surface, okay, so we recognize that the helix angle gamma, this is the shear strain of the element. Okay, so upon application of the torque, no, originally this is a straight line CD, no, so this is distorted into a helix CD prime. So this angle, okay, this angle, so this will be the shear strain, no, of the element. Okay. From geometry, we obtained that arc DD prime. So this is the arc DD prime. Okay, so this is equal to rho d theta, and this is also equal to gamma dx. Okay, so if you are going to recall in our geometry, okay, let's say we have here this sector of a circle, okay, and this is an arc. No, so to solve for the length of this arc, okay, so we can use this formula. So this is equal to theta r. Wherein theta here, class, this is in radian. So this is the angle of this sector. Okay, and r here, this is the radius of this sector. Okay, again, to solve for the length of this arc, this is just theta r. Okay, now, here, no, to solve for this dd prime, to solve for its length, okay, we can use the cross-section or this surface. Okay, so using this cross-section, okay, so for this arc dd prime, no, the radius here, class, no, the radius here is rho. Okay, so that is the radius, and then the angle here, class, is d theta. So that is just rho d theta. Okay, and if you're going to consider naman this surface, no, so the angle here, class, okay, the angle here is gamma, okay, and the radius here, class, this is dx. Okay, so this is dx. Okay, so from here, class, no, from here, uh, we can equate no rho d theta and gamma dx. So equating them, so it will give us a gamma of d theta equal to d theta over dx rho. Okay, so from this equation class, no, so this d theta over dx, this is the angle of twist per unit length. Where theta here class, this is expressed in radians, ha, take note of that. Okay, and if you're going to incorporate Hooke's law, no, so for Hooke's law, that is this is tau, no, so this is shear stress, and this is equal to g times gamma. Okay, so if we are going to substitute this value of gamma here, no, it will become tau is equal to g times d theta over dx times rho. Okay, and take note here, class, that g and d theta over dx, they are independent of this radial distance rho. So meaning to say, the shear stress varies linearly with the radial distance rho from the axis of the shaft. So meaning to say, if the radial distance rho increases, no, the shear stress will also increase. So they will they will vary linearly. Okay, so they are directly proportional, no, the shear stress and the rho, or the radial distance rho. Okay. Okay, so the variation of the shear stress acting on the cross section is illustrated in the figure. Okay, so here in this figure, no, so these blue vectors, okay, so these are the shear stress, no, in this cross section. Okay, so as you can see here, no, at radial distance rho, no, the shear stress is this. Okay, so this represents the shear stress, okay, in radial distance rho. Now, if you are going to notice here, no, from the center, no, as the radial distance increases, okay, the shear stress also increases. Okay, because as we have mentioned, the shear stress, it linearly varies, no, with the radial distance rho. Okay, so as the radial distance rho increases, the shear stress also increases. Okay, and as you can see here, the maximum shear stress will be at the point, no, where this is the this is the outermost surface, okay, of the circular shaft. Okay, so again, the maximum shear stress, it will happen here at the outermost um, surface, okay, of the shaft. Okay, and the radius here will be radius r. Okay, so that maximum shear stress, that will be denoted as this is tau max, no, or the maximum shear stress nga, and it will occur at the surface of the shaft. Okay, now for a shaft to be in equilibrium, let's say for this shaft, no, so there is an applied torque T here, and there will be a reaction torque T prime here. Okay, so for this shaft to be in equilibrium, okay, so let's say we take a section here, okay, and we consider this segment. Okay, so considering this segment, no, this the cross section here, okay, will be shown here. Okay, so this will be the cross section cut here, no, and considering this segment, so what will happen is that there will be an internal torque here. Okay, so this is the internal torque T. Okay, so this is here ha in this cross section. Okay, so here, no, for this shaft to be in equilibrium, the resultant of the shear stress acting on this cross section, it must be equal to the internal torque T acting on this cross section. Okay, so the shear stress, no, represented by this dp, so this is differential force p, no, and then there is a differential area here. Okay, so take note, class, that for shear stress, the formula is the internal shear force over area. Okay, so here, let's say that the internal shear force is dp, okay, and the area is dA. Okay, so to solve for dp, no, using the formula, so that is just tau times dA. Okay, so again, that is from from stress equal to internal force over area. Okay, so this will be the formula for dp. And take note that we derived a formula for tau, and that is g times d theta over dx rho. Okay, so we can substitute that here. Okay, so take note, class, that this dp, okay, this is directed perpendicular, not to the radius. Okay, so this is perpendicular, ha? Okay, so if you are going to take the moment, no, of this dp, no, of this shear force dp about the center O, okay, so this will be multiplied by the moment arm rho. Okay, so this will become rho dp. Okay, and this will also be equal to the value of dp. So the value of dp is this, g d theta over dx rho dA times rho. So this rho will become rho squared. Okay. Okay, so summing up all the differential elements across the cross-sectional area A and equating the result to the internal torque yields this formula. Okay, so here, class, we just factored out g and d theta over dx since they are constants, no? And what will happen here, there will be an integral of rho squared dA here, and this will be equal to torque T. So that is the condition, ha. It should be equal to the internal torque T, no, to make the circular shaft in equilibrium. Okay, so here, class, no, if you're going to recall, in statics of rigid bodies, this integral of rho squared dA, this is actually familiar, right? So this is actually the formula for polar moment of inertia. Okay, and this polar moment of inertia, this is denoted as J. So this integral of rho squared dA, we can substitute J here. Okay, so substituting that value, no, this will now become d theta over dx. This will be equal to t over, so this is g and this is j. Okay, so that will be cross multiplied, so that will become t over jg here. Okay, so from here, we can cross multiply dx here. No? So this will become d theta is equal to t over jg times dx. Okay, so if we are going to integrate both sides, okay, integrating both sides, so integral of d theta, that will just become theta. And this will be equal to the integral, no, of t over jg times dx. And class, notice here, class, that t and gj, they are constants. Okay, so we can just factor them out. And the integral of dx from 0 to L, that is actually the length, the total length. Right? So we can say that this theta, this is equal to TL over jg. Okay, so this is actually the derivation, okay, of this formula. So we are going to use this formula for this topic. So this is the angle of twist. Okay, so this is the deformation, okay, for torsion. So this is theta is equal to TL over JG. Where in this theta, this must be in radian. Okay. So here are some notes on the computation of angle of twist theta. So it is a common practice to let the units of G, or the modulus of rigidity or shear modulus, determine the units of the other terms. Let's say in US customary system, let's say that the unit for G is PSI. We know that PSI, this is pound per inches squared. So meaning to say, all the other terms or quantity, they must all be expressed in pound and inch. Now, let's say for torque T, no, this must be expressed in pound inch. For length L, it must be expressed in inches. And for the polar moment of inertia J, it must be expressed in inches to the fourth. Okay? And also for SI system, let's say the unit for G is Pascal. So Pascal is Newton per meter squared. So all the other terms must be expressed in Newton and meter. Okay, so the torque T, it must be expressed in Newton meter. The length L must be expressed in meter. And the polar moment of inertia J, it must be expressed in meter to the fourth. So this can also be, let's say the unit for G is megapascal. We know that megapascal is Newton per millimeter squared. Okay, so all the other quantities or terms, they must be expressed in Newton and millimeter. Okay, so the unit of theta is radians regardless of which system of units is used in the computation. Okay, and also class, in problems where it is convenient to use a sign convention for torques and angles of twist, we represent torques as vectors. We use double-headed arrows to represent couples and rotations using the right-hand rule. Okay, so as you can see here, class, now let's say for this cross-section, the torque acting here is this torque. Okay, so this is the torque here. So this torque, class, we can also represent this as vector, no, or as double-headed arrow. So this double-headed arrow, as you can see here, this represent this torque. Okay, so also this double-headed arrow, this represents this torque. Okay, same here. This torque is represented by this double-headed arrow, and this torque, this is represented by this double-headed arrow. Okay, so class, to know how to assign the direction of that double-headed arrow that will represent the torque, we are going to use right-hand rule. Okay, so let's say this is our right hand. So let's say for this cross-section, okay, so for this cross-section, the torque here is, this is actually counterclockwise, right? So in our right hand, so the direction, the counterclockwise rotation will be like this, right? So this will be the counterclockwise rotation. Okay, so here, class, the cross-section is here. The cross-section is here, and then the rotation is here. Okay, so this is the rotation. And class, notice the direction of the thumb. Class, the direction of this thumb, this will represent the direction of the double-headed arrow. Okay, again, this is the cross-section. This is the counterclockwise rotation. Okay, so meaning to say, class, if you are going to represent this torque, this counterclockwise torque, as double-headed arrow. So this double-headed arrow, this is pointed away from the cross-section. So this is the cross-section, class. This is the cross-section. Okay, and here, class, as you can see here, the cross-section is here. Okay, and the torque acting at this cross-section is this torque. Okay, so this is my right hand. Okay, so this is the cross-section. Okay, so this is the cross-section. Okay, so class, here, the rotation of the torque is clockwise pala. Okay, so again, this is the cross-section. Okay, so the rotation here, class, is this way. Since the rotation is clockwise, the torque is clockwise. So this is how our right hand will rotate clockwise, right? So class, as you can see here, this thumb, this represents the double-headed arrow. And this double-headed arrow, this is pointing away from the cross-section. Okay, so as you can see here, class, the double-headed arrow here is pointing away from the cross-section because the torque here is clockwise. Okay, so same here, class, same here. Here at this cross-section, class, the torque here, class, is clockwise. So this is the cross-section. This is our right hand. So the rotation, class, is clockwise. Okay, so the thumb, class, this will be the double-headed arrow. And as you can see, this is pointing towards the cross-section. That's why here, this is pointing towards the cross-section. So same here, class. So this is the cross-section. This is the cross-section. And the rotation here is counterclockwise. So using our right hand, the rotation will be like this. And our thumb, it will be pointing towards the cross-section. Right? So that's how we represent torques as double-headed arrows. Okay, so here, class, also, if we are going to use a sign convention, let's say we are going to sum up the internal torques, Class, take note that in our formula, theta is equal to TL over JG. T here. Okay, class, this T, this is internal torque, ha? This is internal torque. So, class, if the internal torque, okay, if the internal torque, if the double, using right hand rule, ha, if the double-headed arrow is pointing away from the cross-section, okay, so that will be positive internal torque. Okay, so same with theta, with the angle of twist, that will be positive. But if the double-headed arrow for an internal torque that is pointing towards towards the cross section, that internal torque and angle of twist, that will be negative. Okay, so that's clear, ha. But class, if you're going to, let's say, sum up torques, in equilibrium equations, we are going to assume that for clockwise torque, clockwise rotation, that will be negative. The positive will be counterclockwise. Okay, so that will be our assumption for summation of torques in equilibrium equation. Positive for counterclockwise and negative for clockwise. Okay. Okay, so let's now talk about shear stress in circular shafts. So this shear stress, this is also called torsional stress in circular shafts. Okay, so from the formula that we derived from the previous slide, we derived this d theta over dx equal to t over jg. And we see that if we cross multiply g here, so this will become g d theta over dx, and this will be equal to t over j. And upon substitution into this formula, so we already derive also this formula. Okay, so if you are going to substitute this g d theta over dx by t over j, it gives the shear stress acting at the distance rho from the center of the shaft. So the shear stress here will become tau is equal to t times rho over j. Okay, so this is the shear stress. Okay, and if you are going to solve for the maximum shear stress, it can be found by replacing rho by the radius r of the shaft. So the maximum shear stress, that will be equal to TR over J. Now for the formula class of polar moment of inertia J for circular shaft. Okay, so this is for circular areas. The formula for that will be equal to pi r to the fourth over 2, wherein r here is the radius of that circular area. And we can also solve this using the diameter. So if in terms of diameter, the formula will be pi d to the fourth over 32. Okay, now for hollow shaft, hollow meaning to say there is a hole here at the center, here at the inner part of the shaft, there is a hole here. Okay, and there will be an inner radius r here, so that will be measured from the center up to this point. Okay, and we will also have here an outer circle. This is the outer circle, Okay, so here there will be an outer radius. Okay, so this will be measured from the center up to the outermost surface of the shaft. Okay, so that will be capital letter R. Okay, and also for the diameter, so this is the diameter of the inner circle, and the diameter of the outer circle will be this capital letter D. So if you're going to solve for its moment of inertia, this will just be pi over 2 times the outer radius r to the fourth minus the inner radius r to the fourth, and it can also be solved in terms of the diameter. So this will be pi over 32 times the outer diameter to the fourth minus inner diameter to the fourth. Okay, so class, if you are going to substitute the formulas of J to the maximum shear stress or tau max, so this will be equal to, for solid shaft, this will be equal to 2t over pi r cubed. Okay, and this is also equal to 16t over pi d cubed. Okay, and for hollow shaft, so this will be equal to 2tr over pi times outer radius r to the fourth minus inner radius r to the fourth, and this can also be equal to 16td. So this is the outer diameter over pi outer diameter to the fourth minus inner diameter to the fourth. Okay, so these formulas, actually class, these are called torsion formulas. Okay, so these are the torsion formulas for solid and hollow shaft. Okay, so the torsion formula, it can be applied using the following procedure. So the first one, you have to solve for the internal loading. Okay, section the shaft perpendicular to its axis at the point where the shear stress is to be determined, and use the necessary free body diagram and equations of equilibrium to obtain the internal torque at the section. Okay, and after that, we have to solve the section property. So we have to calculate the polar moment of inertia of the cross-sectional area. And lastly, now to solve for shear stress, specify the radial distance rho measured from the center of the cross-section to the point where the shear stress is to be found. Then apply the torsion formula. Rho is equal to T rho, or tau rather, tau is equal to T rho over J, or if the maximum shear stress is to be determined, using tau max equal to TR over J. When substituting the data, make sure to use a consistent set of units. Okay. Okay, so let's start solving problem here. Okay, for sample problem number 1, the shaft shown in figure 511A, so this is the figure. Okay, this is supported by 2 bearings and is subjected to 3 torques. Okay, so this is the shaft. Okay, so this is the shaft. Okay, and this is supported by this bearing and this bearing. Okay, and this shaft, this is subjected to this torque. Okay, this torque and this torque. Okay, now determine the shear stress developed at points A and B located at section AA of the shaft as shown in this figure. So class, section AA is located here. Okay, so the zoomed version of that section AA is this, no, is shown here. Okay, so the points A and B, they are located here and here. So point A class, no, so the radius from the center, no, to point A, so that is actually 0.75 inches. Okay, and for distance B, or for the point B, no, the distance from the center to that point, so that is 0.5 inches. So here, class, we are going to determine the shear stress developed at those points, at point A and point B. So let's start solving this problem. Okay, so for this problem, we are going to solve the shear stress developed at points A and B at section AA. So this is the section AA. Okay, so to solve this shear stress, no, we are going to use the formula. Okay, so that formula is T rho over J. So that is the formula for shear stress. Where in T, that is the internal torque. Rho, that is the radial distance. And then J, that is the polar moment of inertia. Okay, so to solve this class, we have to solve first for the internal torque. So we are going to solve the internal torque here at section AA. Okay, so to solve for that, no, we are going to cut this shaft, no, through section AA. Okay, so we can consider either this segment or this segment. And class, take note here that the support, no, of this shaft are bearings. Okay, so these supports are not fixed supports. Class, remember that if it is fixed support, no, there will be a restriction for the shaft to rotate. Okay, so there will be a reaction. There will be a reaction torque. But in this case, class, this is a bearing, okay, and provided that the shaft's weights or weight is neglected, no, we will assume here, class, that the reactions here at the bearings, at the bearing support are 0. Okay, so there will be no reaction here at this bearing and this bearing. Okay, so class, considering this segment, okay, to solve for the internal torque T at section AA, so we cut this shaft here, no, so we are going to consider that segment. So this will be that segment. Okay, and class here, no, in the cut section, okay, so there will be an internal torque T here, and we are going to assume that the internal torque T here, class, is clockwise. Okay, so that's just our assumption, ha. Okay, so class, to solve for this internal torque T, we are going to use equilibrium equation. Okay, so this is just like summing up moments, class, since torques are moment, right? So this is just like how we sum up moments or couples. Okay, so we are going to sum up moment about the x-axis. Okay, so summing up moment about the x-axis. Again, class, our sign convention here, for counterclockwise torques, that will be positive. But for clockwise torques, that will be negative. So in this case, class, summing up moment about or torques about the x-axis, so that will be equal to 0. Okay, so class, this 42.5 kips inch torque, this is counterclockwise. Okay, so this will be positive. And then this 30 kips inch torque, this is clockwise. So this will be negative here. And then the internal torque T, so our assumption is clockwise, so this will be negative T here. And this will be equated to 0, ha? So solving for T, okay, so the answer here, class, is positive 12.5 kips inch. Okay, so the positive sign here, class, indicates that our assumption is correct. That the internal torque T, this is really clockwise. Okay, so from here, class, no, we can now proceed to solving the section property, which is the polar moment of inertia, J. And that is equal to pi r to the fourth over 2. So in this case, class, the radius, class, no, of the shaft. So this is a solid shaft, right? Circular shaft, solid circular shaft. Okay, so the radius, so that is measured from the center up to the outermost surface of the shaft. So that is 0.75. Now the radius. Okay, so substituting that here, so our polar moment of inertia will be pi times 0.75 to the fourth over 2. So that will be equal to 0.49701 inches to the fourth. So after we solve for the internal torque and the polar moment of inertia, now we can now solve for the shear stress developed at points A and B. So starting with point A, okay, so point A, class, is located here, ha? Okay, so using the formula T rho over J, so the rho here, class, will be the distance from the center to point A. So in this case, our point A, class, is 0.75 inches from the center. So that will be the radial distance. Okay, so substituting that in our formula, okay, together with the torque and the polar moment of inertia J, so this will be equal to 12.5 kips inch for internal torque T, and then the radial distance is 0.75 inch over the polar moment of inertia, which is 0.49701 inches to the fourth. Class, make sure that our units here are consistent, ha? Okay, so if here this is inch, so it should also be inches, ha? Okay, so in this case, class, solving this, okay, so if we input this in our calculator, 12.5 times 0.75 over 0.49701, this is 18.863. And the unit for this, class, now as you can see, this is kips inches squared over inches to the fourth. So inches squared will be cancelled, and what will remain in the denominator is inches squared. So this will be kips per inches squared. Okay, so that is also KSI, right? So this will now be the answer for the shear stress developed at point A. Now, for the shear stress developed at point B, class, the radial distance, okay, of point B from the center is 0.15. So that will be our rho. Okay, so let's just substitute that in our formula. Okay, the value of T, again, 12.5 kips inch. The rho is 0.15 inches or inch over the J, 0.49701 inches to the fourth. So solving this in our calculator, 12.5 times 0.15 over 0.49701. So this is equal to 3.773 KSI. So this will now be the answers for this problem. For sample problem number 2, what is the minimum diameter of a solid steel shaft that will not twist more than 2 degrees in a 5-meter length when subjected to a torque of 10,000 Newton meter? What is the maximum shearing stress developed? For steel, use modulus of rigidity equal to 83 gigapascal. So for this problem, we are going to solve the minimum diameter of the solid steel shaft. Okay, and there is a given angle of twist here that is 2 degrees. Okay, and then we have here the length of the shaft, which is 5 meters, and the internal torque, which will be 10,000 Newton meter. Okay, so we are going to solve that, ha? And after that, we are going to solve the maximum shearing stress developed. Okay, so let's start solving this problem. Okay, to solve for the minimum diameter, we are going to use the formula theta is equal to TL over JG. Since the theta is given, that is 2 degrees, but we have to convert that into radians. Okay, so class, the given for theta is 2 degrees, converting that into radian, so this will be multiplied by pi over 180 degrees. So this will be equal to T. So the T here, class, is 10,000 Newton meter. So converting meter to millimeter, okay, so this will be multiplied by 10 cube or 1,000. Okay, times the length, which is 5 meters, so that will be 5,000 millimeter over the j, no? So our j here is pi d to the fourth over 32. So d is unknown here. So this is what we are solving. Okay, times the g. So for g, the given g is 83,000 megapascal. Okay, or Newton per millimeter squared. Okay, so the only unknown here class is diameter. So we can solve for the diameter. So solving for the diameter class, so this will be 115.15 millimeter. So this will be the minimum diameter that we are looking for. Okay, so after this class, now we are going to solve the maximum shearing stress. So we are going to use the value that we solve here, no, the diameter that we computed here. So using the formula for maximum shearing stress, that is tau max equal to T. Our rho here in this case is R, since the maximum, we are solving for the maximum, no, over G. So our R here, class, no, it will be the half of this diameter, right? So let's just substitute the values here. For T, that is 10,000 times 10 cubed to make it Newton millimeter, times the radius. The radius, class, is half of the diameter, okay, over our J. So our J here, class, is pi d to the fourth, which is 115.15 millimeter to the fourth over 32. So solving for the maximum shearing stress, so this will be 33.36 Newton per millimeter squared or mega Pascal. So this will now be the answers for this problem. For sample problem number 3, figure A shows a 2-inch diameter solid steel cylinder that is built into the support at C and subjected to the torques TA and TB. So this is the solid steel cylinder. Okay, so this is supported here at C. So this is a fixed support. Okay, and this solid steel cylinder, this is subjected to torques A. So this is a counterclockwise torque, no? And then we have TB. Okay, this is a clockwise torque. Okay, so for letter A, determine the maximum shear stresses in segments AB and segment BC. Okay, and for letter B, compute the angle of rotation of end A. So end A here, class, this is a free end, ha? So it will rotate. Okay, so class, to solve for that angle of rotation here at end A, we have to sum up the angle of rotation in segment BA and C, or segment AB and segment BC. Okay, so we are going to use the modulus of rigidity equal to 12 times 10 raised to 6 psi for steel. Okay, let's solve this problem. Okay, so to solve for the maximum shear stresses in segments AB and BC, no, we are going to use the formula T rho over J. So we have to solve first for the internal torque T. Okay, so for the internal torque, no, in segment AB, no, so to solve for that internal torque, no, we have to cut this let's say this shaft, no, in at segment AB. So any section here, no, in segment AB, so we are going to cut, let's say, at this section, okay, and we will consider this segment. Okay, so considering that segment, okay, for AB, so this is that cut segment. Okay, so we consider this segment, upon cutting this segment AB here at this section. Okay, so upon cutting that or upon cutting this segment at this section, class, there will be an internal torque TAB here. So this is the the internal torque. So class, the applied torque here is TA, and that is equal to 900 pound-feet. So class, of course, the direction of the internal torque TAB, it should be opposite of the applied torque. So the applied torque is counterclockwise. So of course, the internal torque, it must be clockwise. Okay, to make it in equilibrium. Okay, so class, we can also represent this torque, no, these two torques, okay, we can express them or represent them as double-headed arrow. Okay, so for this 900 pound-feet torque, so using right-hand rule, okay, so the double-headed arrow, it will point away, no, from the cross-section. And for the internal torque, no, so that is clockwise, so using right-hand rule again. So class, the internal torque TAB, that is pointing away, the double-headed arrow, that is pointing away from the cross-section. Okay, so class, if we are going to solve for the internal torque TAB, okay, so we can sum up all the torques here, no, and this will be in equilibrium, so this will be equal to 0. Okay, so for our assumption here, class, for counterclockwise, that will be positive. For clockwise, that will be negative. So this 900 pound-feet torque, that will be positive. And then the internal torque, TAB, that will be negative since it is clockwise. Okay, so this will be equal to 0. So we can solve for TAB, or the internal torque at segment AB. Okay, so the answer for this, class, is 900 pound-feet. So this is the internal torque at segment AB. Now for the segment BC, okay, so we can cut the segment BC, let's say here at this section. Okay, and let's just consider this segment. Upon cutting here, now let's just consider this segment at the right. Now, instead of this segment at the left. If we are going to use this segment at the left, we have to solve first for the reaction torque here at support C. No, so instead we use this segment na lang, no, to simplify the computation here. So class, this will be the right segment, no, upon cutting segment BC here at this section. So there will be a torque here for 100 pound-feet, no, and then the TA, or 900 pound-feet torque. Okay, so here, class, no, there will be an internal torque here, no, where we cut the segment BC. Okay, so this will be the internal torque at segment BC. Okay, so this will be the internal torque, class. Okay, so we have to solve this using equilibrium equation. Okay, and also, class, no, for these torques, no, we can represent this as as double-headed arrows. Okay, so representing this torques as double-headed arrows. So for this torque, no, the double-headed arrows here will be pointing away from the cross section, and then for this, no, so the double-headed arrow here, class, will be pointing away also from this cross section, and also for this, no, so the torque here also, class, or the double-headed arrow, it will be pointing away from the cross section. Okay, so summing up these torques, no, to solve for the internal torque TBC, no, so this will be 900 pound-feet, so that will be positive since that is counterclockwise. For 100 pound-feet, that will be negative since that is clockwise, and negative TBC since that is also clockwise. So this will be equal to 0 since this is in equilibrium. Okay, so solving for TBC, or the internal torque at segment BC, that will be equal to 500 pound-feet. Okay, so after we solve for this internal torques, we are now going to solve the section property, or the polar moment of inertia J. Okay, so for the polar moment of inertia J, this is a solid shaft, no? So its polar moment of inertia will be equal to pi d to the 4th over 32, and the diameter here, class, is 2 inches. Okay, so our polar moment of inertia will be pi times 2 to the 4th over 32. So if you input that in your calculator, that will be 1/2 pi, or 1.5708 inches to the 4th. So after we solve for the internal torque and the section property, or the polar moment of inertia, we can now solve for the shear stress. Okay, so solving for the maximum shear stresses in segments AB and BC. For segment AB, so that will just be equal to the internal torque at segment AB times the radius, no, over the polar moment of inertia. So substituting the values here. The internal torque class is 900 pound-feet, no? So let's convert this feet, no, into inch by multiplying this to 12 inch, no, times the radius. So the radius here, class, is 1 inch since the diameter is 2 inches. Okay, over the polar moment of inertia, that is 1.5708 inches to the fourth. So solving this will be 6,875.48 pound per inches squared. Okay, or PSI. So this will be the answer for the maximum shear stress in segment AB. Now for segment BC, that will just be T or the internal torque at segment BC times R over J. So the internal torque at segment BC, that is 500 pound-feet. So we just convert feet into inch. So we will multiply this by 12. And then times the radius, that is 1 inch over 1.5708 inches to the fourth. So this is the J, no, or the polar moment of inertia. So solving this, so the maximum shear stress at segment BC, this is equal to 3,819.71 PSI. Now, for letter B, now we are going to solve for the angle of rotation of end A. So again, end A, class, this is a free end. So this will have the freedom to rotate upon the application of the torques. Okay, here. Okay, so class, we are going to sum up, no, the angle of rotation or angle of twist, no, of segment AB and segment BC. Okay, so to solve for the total angle of rotation here at end A. Okay, so class, for the angle of rotation at segment AB, okay, so class, we are going to consider here the sign convention for angle of twist or internal torques. Okay, so in this case, class, the internal torque here, so the internal torque here is this TAB, right? So the class, this internal torque, no, represented by this double-headed arrow. So this double-headed arrow, this is pointing away from the cross-section. So meaning to say, this internal torque, this is positive, right? That's why it will be positive. Okay, this angle of twist in segment AB, this will be positive. Okay, now for segment BC, so this is the free body diagram, no, of the segment, no, if we cut a section here at segment BC, and the internal torque here is here. Okay, and the internal torque here also, class, no, as represented by this double-headed arrow. This double-headed arrow, this is pointing away from the cross-section. Okay, so this torque, this is also a positive internal torque. Okay, so meaning to say the angle of twist, no, in segment BC, it will also be positive. Okay, so that's our sign convention, class, ha? Okay, so from here, class, no, we will just substitute the values for internal torque, the length, the polar moment of inertia J, and the modulus of rigidity G to solve for this. Okay, so substituting the values here, class, for segment AB, the internal torque is 900 pound-feet, so converting that into inch, no, so we will multiply this by 12, times the length. So the length, class, of AB, this is 5 feet. So converting that into inch, so we will multiply that by 12 over the polar moment of inertia J, that is 1.5708 inches to the fourth, times G. So the G here, class, is 12 times 10 raised to 6 PSI. Okay, so that's why we convert the units here, ha, and we make it pound and inch, no, since the value or the unit for G is pound per inch squared. Okay, so it has to be consistent. Okay, so now for the segment BC, okay, so the internal torque for that is 500 pound-feet. So converting that feet into inch, so we will multiply this by 12 times the length. So the length, class, of segment BC is 3 feet. So that will be 3 feet. Converting that to inches, we will multiply this by 12. Okay, over the J is just the same. and same with G, no, it will just be the same. Okay, so class, solving this in your calculator, no, so this will give us a theta A, or angle of rotation at end A, equal to 0.045837. And the unit for this class, regardless of the system, so this will be in radian. Okay, so this will now be the answers for this problem. Okay, so let's now move on to power transmission. Okay, so in many practical applications, shafts and tubes having circular cross sections are often used to transmit power developed by a machine. When used for this purpose, they are subjected to a torque that depends on the power generated by the machine and the angular speed of the shaft. Okay, so if we are going to define power, so it is defined as the work performed per unit of time. Okay, so the power P transmitted by a torque T rotating at the angular speed omega is given by this formula. So this is power P is equal to torque T times angular speed omega. Okay, we're in the omega here, no? This is measured in radians per unit time. Now, if the shaft is rotating with a frequency of F revolutions per unit time, then we can rewrite omega as 2 pi F. Okay, so if we are going to substitute this omega, no, from this formula, so power now becomes T times 2 pi F. Okay, wherein if we are going to solve for the torque, no, the formula for torque will be equal to P over 2 pi F. Okay, so class, in SI units, no, the power P here, class, no, its unit should be in watts. And take note that 1 watt, no, this is equal to 1 Newton meter per second. Okay, and for the frequency F, okay, so this should be in hertz. Okay, and take note that 1 hertz, no, that is equal to 1.0 revolution per second. Okay, so from this formula, class, no, if you are going to use these units, no, so the torque T here will be in Newton meter. Okay, now in US customary units, no, or in English system, okay, so P, it should be in horsepower. Okay, and the frequency F, it should be in hertz. Okay, so for horsepower, take note, class, that 1 horsepower, that is equal to 550 pound-feet per second. Okay, so if you are going to use these units, no, for this formula, so the torque T here, class, will be in pound-feet. Okay, so class, also take note of these conversions, that for 1 HP, this is equal to 746 watts. And Newton meter, class, this is also equivalent to joule. And for 1 British thermal unit, or BTU, this is equal to 1055.056 joules. Okay. Okay, so let's solve sample problem. A solid steel shaft AB shown in the figure is to be used to transmit 5 horsepower from the motor M. So this is the motor M, to which it is attached. If the shaft rotates at angular speed omega equal to 175 revolution per minute, and the steel has an allowable shear stress of 14.5 kSI, determine the required diameter of the shaft. Okay, so let's solve this problem. Okay, so for this problem, we are going to solve the required diameter of the shaft. Okay, so in order for us to solve this required diameter, now we have to solve first, no, the torque, no, using this formula. Okay, so after we solve for this torque, okay, we can use the given allowable shear stress, no, to design the diameter, or to compute the required diameter. Okay, so class, here, if you are going to use this formula, P is equal to T times omega, power P, so this is given in the problem, and also the omega, this is also given. So we will just substitute the given values for P and omega to solve for the torque T. Okay, so class, the given power P is 5 horsepower. So we have to convert this refers to feet-pound per second. So for every 1 HP or horsepower, that is equivalent to 550 feet-pound per second. So computing the power P, so this is 2,750 feet-pound per second. Now for the omega, the given omega is 175 revolution per minute. Okay, so we have to convert this revolution per minute to radian per second. No, so converting this revolution, so for every 1 revolution, there is 2 pi radian. Okay, and for every 1 minute, there is 60 seconds. No, so computing this omega, so this will be 18.326 radian per second. Okay, so this will be the angular speed. Okay, now, since we already have P and omega, we can now solve for the torque. No? So, substituting the values for P, so that will be 2,750 equal to the torque T, and then the omega, which is 18.326. Okay, so from here, we can now solve the torque, and the value of torque is 150.06 feet pound. Okay, so from here, class, we can now we can also rewrite this torque no in inches kips or kips inches. Okay, so this will be 1.80072 inch kips or kips inch if we convert this feet pound to kips inch. Okay, so class, from here, no, from this formula, no, as we know, this is shear stress equal to torque times radial distance rho over J. No, so we are going to use this. No, so there is a given allowable shear stress. No, so we will substitute that here in this shear stress. Okay, so this will be allowable shear stress equal to torque times rho over J. Okay, so the value of rho, T rather, we already have that. Okay, and for the allowable shear stress, that is also given, that is 4.5 KSI. So this is the given allowable shear stress. That's why we converted torque T to kips inch. Okay, so that will be consistent no in our units here. And then the rho here, class, this is the radius, okay, of the shaft. Okay, so this radial distance or radius, no, so this is measured from the center of the shaft, okay, to the outermost surface, okay, of the shaft. Okay, over J. So J here, class, the polar moment of inertia for a solid circular shaft, that is pi radius, which is the rho here, no, to the fourth over 2. Okay, so we can now solve rho from here. Okay, so this rho in the numerator, it can be cancelled, and this rho to the fourth, it will become rho cube. Okay, so we can now solve rho cube or rho no by um, 1.80072 divided by 14.5 times pi over 2, and then the answer for that, we will get its cube root, no, since this is rho cube. Okay, so solving for rho, this will be equal to 0.42919 inch, no. So the unit for this class is inch since this is inch here and then inch here. Okay, so this will now be the radius. But take note, class, but that what we are going to solve here, class, is the required diameter. So this is just the radius. So to solve for the diameter, no, we are just going to multiply this radius by 2. Okay, so solving for the diameter, that will just be 2 times 0.42919 inch. So the diameter here, class, will be 0.85839 inch. So this will now be the answer for this problem. Okay, so let's proceed now to statically indeterminate problems in torsion. So a torsionally loaded shaft may be classified as statically indeterminate if the moment equation of equilibrium applied about the axis of the shaft is not adequate to determine the unknown torques acting on the shaft. An example of this situation is shown in figure A. So as you can see here, class, we have here this shaft AB. Okay, and both ends of this shaft are fixed supported. So this is fixed supported at end A and fixed supported at end B. Okay, and we have here this applied torque T. Okay, so class here, no, if this shaft, no, if both of its ends, no, are fixed supported or restrained, so that means to say that upon application of this torque, there will be reactive torques, no, in both ends since they are both restrained. Okay, so as shown in the free body diagram in figure B, no, these reactive torques at supports at A. Okay, so this will be the reactive torque at A, and this will be the reactive torque at B. Okay, so they are both unknown. Okay, so they are both unknown. So if you are going to apply equilibrium equation here, class, not to generate an equation, there will be just one equation, and that will be the moment equation. Okay, so summing up moment, no, about the axis of this shaft, no, so that will be equal to 0 since we are in equilibrium. And class, our sign convention here is positive for counterclockwise rotation and negative for clockwise. So in this case, class, T will be positive minus TA minus TB. So both TA and TB are negative since we assume them as clockwise. Okay, so this will be equal to 0. So take note, class, that there will be two unknowns here, TA and TB. Okay, but this is the only equation or moment or equilibrium equation that we can generate. Okay, so we are going to generate another equation using compatibility. Okay, so in order to obtain another equation, we will use a necessary condition of compatibility or the kinematic condition. Okay, so the compatibility requires the angle of twist of one end of the shaft with respect to the other end to be equal to 0, since the end supports are fixed. Okay, so class here, take note that both ends are restrained to move. So meaning to say there will the angle of twist, okay, at both ends will just be 0 if we sum them up. Okay, if we sum up, class, the angle of twist of segment AC and segment CB, they will be 0. Okay, so they will be 0. Therefore, class, no, the angle of twist, no, of this segment AB, okay, it will be 0. Okay. Okay, so from this compatibility, provided that the material is linear elastic, we can apply the load displacement relation theta is equal to TL over JG to express the compatibility condition in terms of the unknown torques. So realizing that the internal torque in segment AC, so as you can see, class, no, in segment AC, so this is the segment AC, right? Okay, so if we are going to cut this here, no, just to know the internal torque in segment AC. So this will be the internal torque. And as you can see here, class, this internal torque in our sign convention, now if this is the cross section, its rotation is counterclockwise, right? So that is counterclockwise. So class, notice here that the thumb, which represents the double-headed arrow, no, so this is pointing away from the cross section. Okay, so that means to say that the torque, this internal torque, no, in segment AC, this is positive, right? So this will be positive. And in segment CB, so this is the segment CB, if we are going to cut this segment here in this section just to solve for its internal torque, so its internal torque, class, will be this torque. Okay, so this torque, class, no, so if this is the cross section, so let's say this is the cross section, and the rotation of the torque is actually clockwise, right? So that is clockwise. Okay, so that is clockwise. And notice here, class, that the thumb, which represents the double-headed arrow, so this is pointing towards the cross section. Okay, so in this case, class, no, the internal torque here in segment CB, this is negative. Okay, so from here, class, no, if we are going to sum up the angle of twist of segment AC and segment CB, so this will be the angle, no, or the angle of twist in segment AC. So this will be minus the angle of twist in segment CB. And this will be equal to 0. Okay, so since there will be no um, angle of twist in both ends, no, since they are restrained in both ends, at both ends. Okay, so from here, class, no, we can express this angle of twist in terms of TL over JG. So substituting this, class, no, so this will become TA and then length AC over JG minus TB length CB over JG is equal to 0. So class, this will now be the second equation that we can use. So this will be in terms of TA and TB. Okay, and then using this equation and the equation from the equilibrium equation, no, so we can solve for TA and TB. Okay. Okay, so here's the summary of the procedures, okay, in solving statically indeterminate problems in torsion. So the first step, you have to draw the required free body diagrams and write the equations of equilibrium. The second step, you have to derive the compatibility equations from the restrictions imposed on the angles of twist. And for the third step, use the torque-twist relationships in theta is equal to TL over JG to express the angles twist in the compatibility equations in terms of torques. And lastly, you can now solve the equations and compatibility for torques. Okay. Okay, so let's now solve this problem. The shaft in figure A consists of a 3-inch diameter aluminum segment that is rigidly joined to a 2-inch diameter steel segment. So this is the 3-inch diameter aluminum. Okay, and this is the 2-inch diameter steel segment. So the ends of the shaft are attached to rigid supports. Okay, so these are fixed supported here at this end and also here at this end. So calculate the maximum shear stress developed in each segment when the torque T is equal to 10 kips inch is applied. Okay, so this is the applied torque T. Okay, so use modulus of rigidity equal to 4 times 10 raised to 6 psi for aluminum and for steel that is 12 times 10 raised to 6 psi. So let's solve this problem. Okay, so for this problem, class, we are going to solve the maximum shear stress developed in each segment. So that will be the aluminum segment and the steel segment. Okay, so, but before we solve for that shear stress, we have to solve first for the torques here. Take note, class, that this rod, this composite rod, this is fixed supported at both ends. So this is fixed supported here and fixed supported here. So that means to say that there will be two reactive torques here. No, there will be a reactive torque here and a reactive torque here. So those reactive torques, they will be unknown. Okay, and take note here, class, no, that we can only generate one equilibrium equation here, and that is the summation of moment. Okay, so that means to say that this is statically indeterminate. Since that equilibrium equation, that one equilibrium equation, that will not be enough, okay, to solve this problem. So we are going to use compatibility here, ha. Okay, so again, first we have to generate the equilibrium equation. So this will be the reactive torques. Okay, so here at this end, no, so this will be T sub AL, or the reactive torque here at the aluminum segment. Okay, and at the end of this steel segment, no, so there will also be a reactive torque here. So this is T sub ST. Okay, so generating the equilibrium equation here, class, so that will be summation of the moment here at this axis. So this is the axis of the shaft. So this is the x-axis. No, so this will be equal to 0 since we are in equilibrium. Okay, so our sign convention, class, here is positive for counterclockwise and negative for clockwise. So this 10 kips inch, no, so this will be positive, and we are going to convert kips in pounds, ha, so this will become 10,000 pound inch, and then both TAL and TST, no, we assume them as clockwise. They are both clockwise, so they will be both negative here. So this will be equal to 0, and this will serve as our first equation. So we have to generate another equation by using compatibility here, class. Okay, so take note, class, that they are both fixed, no, at both ends, no, for this shaft. Okay, so what will happen here, class, is there will be no angle of twist, no, at both ends, since they are both restrained. Okay, so what happens here, class, is that this the uh, the angle of twist in aluminum segment, that should be equal to the angle of twist of the steel segment for the angle of twist to be 0 if we sum them up. Okay, so that means to say that the angle of twist in the steel segment, that will be just equal to the angle of twist here in the aluminum segment. Okay, so if we transpose this, this will just be theta st minus theta al is equal to 0, right? So that is just an equivalent equation. Okay, so from here, class, no, what happens here is that we are going to express this angle of twist, no, in terms of TL over JG. Okay, so this will be for the steel and this will be for the aluminum. And we are just going to substitute the values here for the length of the steel. No, so this is the steel. Okay, so this is the steel. So this is 3 feet. And we will just convert this in inches. So 3 feet times 12, that will be 36 inch. Over our polar moment of inertia for steel, class, no? So its diameter is 2 inches. Okay, so the formula for that is pi d to the fourth over 32. And our diameter here is 2 inches. Okay, and for our modulus of rigidity, this is given, no? So for steel, this is 12 times 10 raised to 6 psi. Okay, so we have to be consistent how with our unit. So this is psi, so this should be in inch, and this should be in inch. So our torque here will be in pound-inch. Okay, so same here with the aluminum. So the length of the aluminum, class, is 6 feet. So times 12, that will be 72 to convert it in inch. Okay, over the polar moment of inertia, class, of the aluminum. Okay, so that will be pi d to the fourth over 32, wherein the diameter here, class, is 3 inches. Times the modulus of rigidity, which is 4 times 10 raised to 6 psi for aluminum. Okay, so class, from here, no, we can now simplify this. So simplifying this, no, so this will become 0.0000019099 TST is equal to, for this, so this will become 0.000000222635 TAL. So solving for TST in terms of TAL, dividing both sides by this coefficient. Okay, so this will now become 1.18516 TAL. So this will now serve as the equation 2. Okay, so solving equation 1 and equation 2 simultaneously, now we can substitute this TST to equation 1, so that TAL will be the only unknown. So we can now solve for that. Okay, so we substituted TST here. No, so this will become this equation. And solving for TAL, class, or the torque in the aluminum segment, so this will be equal to 4,576.32 pound-inch. Okay, so after that, class, now we can now solve for the torque in the steel segment by substituting this computed value of TAL here. Okay, so TST will now become 5,423.68 pound-inch. So class, here, the values of the torque in the aluminum segment and in the steel segment, they are both positive here. So that means that our assumption that for torque in aluminum and steel, they are both clockwise. So that is a correct assumption. They are really clockwise. Okay? So from here, class, no, since we already solved for the torque, now we can now solve for the shear stress. So we are going to use this formula. So this is shear stress equal to TR over J, wherein T here is the internal torque, R is the radius, and then J is the polar moment of inertia. Okay, so for the steel, okay, so the internal torque for steel class is 5,423.68 pound-inch. Okay, and the radius here class, so the diameter is 2 divided by 2, so that will be 1 inch for the radius over the polar moment of inertia. So pi diameter is 2 inch to the fourth over 32. So solving for this class, this will now be the maximum shear stress in the steel segment. So this is 3,452.82 psi. Okay, so this will now be the answer for that. Now for the maximum shear stress in the aluminum segment. Okay, so this will have the same formula. So substituting the torque here. So the torque or the internal torque for the aluminum, that is 4,576.32. Okay, so that will be multiplied by the radius, which is 3 divided by 2. So that will be 1.5 inch over its polar moment of inertia, pi, times its diameter, which is 3 inches to the fourth over 32. So solving this, this will be 863.22 psi. So this will now be the answers for this problem. Okay, so this is for bonus points. So what you're going to do is just answer the questions that will be flashed in your screen. Okay, and you just have to comment in the comment section your name, your section, the item that you are answering, and your answer. And don't forget the unit of your answer. So this will be the questions. Okay, so for number 1, if the internal torque TA is equal to 13 kips-inch and the diameter of the shaft is 1.65 inch, determine the maximum shear stress in the cross-section. And for the second question, if the internal torque TA is equal to 10 kips-inch and the allowable shear stress at the cross-section is 20 ksi, determine the required diameter of the cross-section. For the third question, if the internal torque of a 100 millimeter solid steel shaft segment of length 5.45 meter is 13 kilonewton meter, what will be the angle of twist in radians? Use modulus of rigidity equal to 83 gigapascal. And for the last question, determine the torque if the power P is 800 watts and the frequency F is 185 revolution per minute. So the first students who will be able to comment the correct answers, okay, will receive the bonus points. So maximum of 2 answers or 2 bonus points for every student. So I hope that you get the bonus points, class. So that concludes our discussion for this topic. I hope that you learned and attained the learning outcomes. And see to it, class, that you answer the CM assessment task for this topic, and it will be submitted on our next meeting. So see you again, class, on our next meeting. Keep safe. God bless, class. Bye-bye.